And then, yeah, please go ahead, Yuri.
All right, hello everyone. Thanks for coming. So today I'm going to talk about solitons for the flows, which we have been discussing for a while already. So specifically, I'm going to discuss today and next time solitons in dimension 4. So maybe let me start with a little speculation about geometric flows in general to explain why we care about solitons. So if you have some manifold and some geometric data on it, so maybe this geometric data will be just a metric, and you have some sort of flow for the metric, maybe it's a Ricci flow. Then what you really want to understand in many cases is what happens with the metric along the flow, whether it converges to something nice, whether it develops singularities, and how exactly it happens. And often the problem is with such a flow, specifically this problem exists for the Ricci flow, that the object to which you converge, whatever sense of convergence you choose, actually depends on your initial data. So for example, you have Ricci flow and your dimension is at least 3. Then what could happen, you can start with some object, maybe it's a 3-dimensional sphere with some initial metric, and you run the flow, maybe you normalize it appropriately that your volume is fixed. Then as time goes to some maximal time of existence, which might be infinity. So specifically for Ricci flow, what could happen that you either converge to round smooth metric, and this is sort of ideal scenario which you're looking for, or you can develop some singularities, and singularity is a typical singularity for the Ricci flow is this neck pinching. You have this very thin neck, which pinches as the flow runs. And this type of behavior it could occur in dimension 3 and higher, and there is really no way to tell apart from the beginning, looking at the initial data, whether you will arrive in one case or the other. So somehow there are some special geometric circumstances and special flows for which we are in much better shape and we can converge to something canonical no matter what we start with. And this is something Jeff mentioned a couple lectures ago. And I'll just reiterate this. So in contrast to this behavior which I have discussed, for example, if you run Ricci flow or Keller-Ricci flow, you can call it if you like, in dimension 2, then you converge to constant Gauss curvature metric. Or if you run, for instance, Keller-Ricci flow on Calabi-Yau manifold, it means that C1 is 0. Then you converge to Calabi-Yau metric, where Ricci curvature is 0. More related to what we are discussing, if you take pluriclosed flow and you run it on something with a flat background on the torus, starting with any pluriclosed metric, then you will converge to the flat metric. So these are examples where the behavior of flow is doesn't really depend on your initial data, and we hope this is, I guess, from the evidence which we have in this very kind of scarce set of examples, that similar thing happens on many other backgrounds for pluriclosed flow, and that we can use it to identify some canonical limiting metric. So specifically, if you want to study the flow, okay, maybe focus for a second on generalized Ricci flow. I recall that as input you take manifold, Riemannian metric, and closed free form. So under generalized Ricci flow, what we discussed a while ago, that you have this functional, and associate a functional to metric, free form, and smooth function. So it's the scalar, you integrate scalar curvature minus norm of torsion plus norm of gradient f against the special volume form. So this is Perelman functional. Appropriately modified for generalized Ricci flow. And then you can construct a single scalar quantity lambda, which will be the infimum of this functional among all choices of functions. Such as this function is appropriately normalized, specifically that this volume is fixed, say constant. And then this will be a functional of metric and free form, and the theorem tells us that this quantity is not decreasing along generalized Ricci flow. So one behavior which you could expect for the flow in this case, if you get a quantity which is non-decreasing, that you will get some limiting objects where this quantity actually approaches a constant. And such quantities, they first indeed occur. We will see a lot of examples of such. And they satisfy a nice set of equations. So specifically, so this quantity lambda of G on H is stationary under the Ricci flow, generalized Ricci flow, precisely on steady gradient generalized Ricci solitons. These solitons, these are structures satisfying a system of equations. First equation is like this. So it's a system of equation for the metric and the free form. And it incorporates a new geometric quantity f here. So f here will be a function satisfying together this set of equations. So whenever you want to solve a flow, and whenever you want to describe its possible limiting behavior, you must also understand solutions to such equation. Because if you have such data, then what the flow does, it only modifies your initial data G and H by a flow of one parameter family of diffeomorphisms. So geometrically, your structure doesn't change up to action of diffeomorphism group, but from the point of view of the flow, which you're considering, you get a non-trivial flow. So such structures are not stationary under the flow, but they're stationary once you mod out by the diffeomorphism group. And again, to understand really the behavior of the flow, you have to understand the structure of such solitons.
Could I ask a question?
Yes.
What is the H star H?
Yes. So there's a question about this term. This is something I think Jeff usually writes as like H squared IJ. This is really the only possible non-trivial contraction of the 3 form with itself, which will give you a symmetric 2 tensor. So if you would like to write it in index notation, it will be I, J, sorry, I, L, S, H, J, L, S.
So I have a question as
Yes.
well. So how did you derive the soliton equation from the stationary property of lambda?
So this function e to the minus f, it's actually the lowest eigenfunction of the appropriate Laplace operator, include which you can cook up from this function. And if you write variation of this flow under the generalized Ricci flow, then you will have exactly the square norms of these 2 terms appearing, with f being this lowest eigenvalue of this Laplace, the second order operator. So if your lambda is stationary, these 2 terms must vanish.
So you use the evolution of your functional along the flow, and
Yes. And that you have this associated to actually any data G and H, you always will have this smooth function which minimizes this functional. So minimizing this function will be actually e to the minus f will be a positive function solving an appropriate functional and minimizing an appropriate functional. So that's probably answering how you can recover a function f if you're given just G and H. Okay. So yeah, I think evolution of this functional f is something Jeff has derived some time ago when we just discussed generalized Ricci flow in general. So are there more questions? So now what I want to do, I want to specialize to some distinguished geometric setting in which such backgrounds occur, and this is specifically plurally closed complex geometry. Recall that if you have a complex manifold with a Hermitian metric, complex manifold, and G is Hermitian, then it is called plurally closed. If DDCI of omega I is 0, where omega I is a fundamental 1-1 form. So why such structures are relevant to us, and why we actually hear about them? So the main reason will be the main motivation which we're getting for it is from the studying of complex surfaces, and I recall to this end the result of Godushon. Even any Hermitian manifold there exists unique conformal factor such that e to the minus f is pretty close. When I say unique, it's unique up to adding a constant. Adding constant to phi just multiplies the entire metric. Sorry, I should.
In complex
Is Godushon is so such that
okay.
so in particular if n equals 2, there exists unique phi such that e to the phi omega I is fully closed. Okay. Again, uniqueness up to adding a constant to this function. So which means what if you take any surface with any compatible Hermitian metric, you can always find the unique conformal representative of this metric, which will be pluriclosed. It means that if you want to study complex surfaces, you really want to first, it makes sense to study it with pluriclosed metrics, since it's a nice approximation of a Keller property, which you lack in general on general complex surface. So this brings us to the question which we want to discuss. That is, what does pluriclosed flow do on a complex surface with pluriclosed metric? So the flow will necessarily preserve this pluriclosed condition. So we'll have some flow of pluriclosed metrics. And a natural question which we could ask is, what will be the limiting behavior? What will be the long time existence? What types of singularities we could run into? And pluriclosed flow is a particular case of generalized Ricci flow, as mentioned above. Is generalized Ricci flow for G and H, which is just dCi of omega I. So all previous discussion, all the comments which we made about generalized Ricci flow, they automatically apply to the pluriclosed flow. In particular, we need to understand the solitons for pluriclosed flow, because solitons, this is the typical example of stationary point modular diffeomorphism for this pluriclosed flow. So before we proceed, let me formulate the following little proposition, which explains the complex geometric significance of the soliton equation. assume that for GI is a fully closed soliton. So by fully closed soliton, I mean that G and H solve the system which I wrote before. So this system, it makes sense on any manifold with a Riemannian metric G and a free-form H. But in the case when this G and H come from a closed structure, it actually has much more information to it from the point of view of complex geometry, and that's what I wanted to formulate. So let's introduce a vector field, which you can normalize differently. Choose this normalization. So where this theta I is the leaf form. Oops. Let's say leaf form, which in dimension 4, in real dimension 4, complex dimension 2, is characterized by the identity with a star of H. Then let's consider these two equations. So we can look at these two equations and we can split them by holomorphic type. So this is equation for a symmetric tensor. So we consider 1 part of the symmetric tensor and 2 0 plus 0 2 part of the symmetric tensor with respect to complex structure I. And similarly for this equation for a 2 form. And it turns out that these 4 equations, so if you split those 2 equations by type, they will provide, they will have a very natural description in terms of this vector field of V. So let me write it down. So if you take equation 1 and take its 2 0 part, then it will be equivalent to the fact that the derivative of your metric with respect to vector V, again, 2 0 part of this vanishes. So if you take first equation and take it 1 1 part, then it will be equivalent to the identity that the derivative of the metric plus Bismuth curvature of I. Okay, here 1 1 equals 0. And similarly, you can do a similar procedure for the second equation. So the second equation, 2 0 part of it is equivalent to the fact that the derivative of omega I 2 0 equals 0, and finally the 1 1 piece of the last equation tells us that the derivative of I V in the direction of IV of omega I 1 1 part equals 0. But they do not look much better than what we had before, but they actually can be reassembled very nicely. So for instance, these two equations, they merely explain you that V is a real holomorphic vector field. So these two equations, they really imply that the derivative of complex structure is 0. Actually, they're equivalent. So the system of these two equations is equivalent to the fact that the derivative of I is 0. So with this knowledge that the derivative of V, that V is real holomorphic, this will imply that IV is just a equivalent vector field. And this will be a separate equation, which I can rewrite as, for example, the derivative of omega I equals rho I 1 1. bottom line, that the right hand equations altogether are equivalent to the following two. First, that VIV is scaling and real holomorphic, that is preserves complex structure. And the derivative of this fundamental 1-1 form is the bismuth curvature 1-1 part of it. So really, when we will be speaking about solving Soliton equation on complex surfaces with fluid closed data, we will be solving these two equations. So we'll be looking for a holomorphic vector field V, which is also Keeling, in which solves this equation. Okay.
Oh, wait, sorry, Yuri. I thought, do we not explicitly get like a PDE for the like 2-0 part as well? Or I mean, there's like one implicit, I guess, but
Yeah, so 2-0 part of bismuth curvature, I guess you mean. Well, it's
of Bismuth
implicitly,
Ricci.
you know, of bismuth Ricci, yeah. It's implicitly hidden here.
I guess for the examples we know, isn't it just that the lead derivative that LV omega I is just Bismuth Ricci, not Bismuth Ricci 1-1? Or is that not right?
No, because I mean, 2-0 part of bismuth Ricci will not be 0. I mean, left hand side is 1-1 form because V is holomorphic.
Yeah.
So the right hand side also must be 1-1 form. And in the examples which we have, this bismuth Ricci is not necessarily of type 1-1.
Okay.
So is this 4-dimensional strictly, or
No, yeah, I formulated in 4 dimensions. It works in general. So you just need to define what leaf form is in general. But yes, all this discussion works for any fluid closed structure. So this derivation is sort of a brute force calculation, but in the end you get this nice structure that always fluid closed soliton really supplies you with a Keeling and real holomorphic vector field. In complete
So
analogy,
one question. So if you have a solution of the last equations on the right hand side, why do you know that IV, that one, why do you know that IV minus the leaf form, so why do you know that V minus the leaf form is a gradient vector field?
Yeah, that's a good question. We don't have a general argument for that. There is actually, the answer is twofold. So first, that it's not necessarily true, because you might have some extra symmetry group on your manifold, some kind of spontaneous symmetry for I, J, and G, and you might just add this vector field to your IV, and then the extra term will not be gradient, will function. Okay. I hope it makes sense. However, what we have in all examples, and I don't have honestly a good explanation for it, probably it should be true in general, but no examples we have that if you come up with a solution to this equation, then there is always a choice of a vector field V here, which puts it into this form.
But strictly speaking, to have an equivalence, you need to add this further condition that.
Yeah, maybe I should add it here. Yes. Mario, does that answer your question?
Yeah, sure. Yeah, thanks.
Okay. All right.
Sorry,
So
can I just ask to clarify? Are you saying that the soliton equations are equivalent to this existence of V of this form that satisfies these two equations?
yes.
But you need to specify the function f or something, or
Yes. I would describe it as follows. So you need to be able to find the holomorphic vector field V such that IV is scaling, and the difference of V and theta I sharp is a gradient of a function. But yeah, this function it sort of will be implicitly defined by the choice of V of a matrix. So as long as you have V and a metric, you will implicitly have this function defined. So the way, maybe let me, before we proceed, let me explain the way we will construct all the solitons. So we really will be solving only these two equations. And then for all the solutions which we will find, we will verify sort of manually, we will provide such function f, which will satisfy the first equation. And of course, it will be nice to see this equivalence without this first assumption. But again, as I have mentioned, formulating it is a bit tricky because you can change your vector field V if you, for some reason, have extra symmetries.
In the Keller case, this first condition would be really equivalent that you have some zeros or something, really very mild topological.
Yes. Yeah, I mean, I believe in this case it also will be a mild topological assumption which will allow to rule this out.
So you probably want that V minus theta I has a 0 or something?
It's actually, yeah, that's an interesting suggestion. In compact case, probably, but yeah, something like this also happens to be true in non-compact complete cases. So I'm still not quite sure what exactly to ask additionally to get rid of this extra assumption.
I mean, I guess, right, if you can like justify the variational calculation of the functional, I mean, I think this is enough, right? I think to recover the function f.
Yes, yeah, this should be enough. Yeah, if you can show that if you know that your functional lambda is constant, then you should be able to recover the function f, and you should be able to come up with maybe a different vector field, I don't know, W, given by this formula, which will also be Keeling and real holomorphic, and it will give you another Keeling holomorphic vector field on the same background. Okay, so this is general observation. Now I'm going to move on to constructing and discussing the existence of solitons on complex surfaces. And before I proceed, maybe let me give you one example of a concrete example where soliton equations are satisfied. So this example will be standard Hopf surface, which again, I believe appeared before in these lectures. So we can take C2 minus the origin, and we can quotient it by group gamma, which is generated by contractions. So you take Z1, Z2, your coordinates in C2, and you send it to alpha Z1 and beta Z2. And let me remove standard here and just describe diagonal. So where alpha and beta are two complex numbers with norms less than 1. So then this manifold, as a complex manifold, let me call this complex structure I alpha beta. As a smooth manifold, it's just diffeomorphic to S3 cross S1. And it is never Keller for no choice of alpha beta and for no choice of a compatible metric, because second homology group vanishes. Somehow, if norm of alpha equals norm of beta, and this is what is called diagonal example, sorry, a standard Hopf. Then there is this very nice distinguished metric, which is Euclidean metric in C2, scaled by the factor Z1 squared plus Z2 squared. So this descends to a metric on M. And for this metric, you will have that M G naught I solves soliton equation. With F equals 0. So we just have Ricci minus 1 force H star H equals 0 and D star H equals 0. Where in this case, actually, H will be just the volume form on the 3 sphere. And theta will be its dual, it will be the volume form on S1 factor. So this is there is this nice example of a soliton, even though it's sort of trivial from the point of view of solitons because your function f is 0. Nevertheless, it's an explicit solution to that system. And it's natural to ask a question of what happens if alpha is not beta, if the norm of alpha, sorry, is different from norm of beta. This metric doesn't define a nice metric on M anymore. It doesn't descend to the quotient. And the question to ask here is, do they exist? What does pluriclosed flow do on these backgrounds? Does it converge to anything nice? And if it converges, again, general expectation that it should be a soliton. So if it should converge to a soliton, we might be able to construct a soliton on this background by hand on Hopf surfaces. And that will be our kind of main construction, which we're going to discuss today.
Sorry, so this argument on standard Hopf, it actually works for Weissman for metrics where the Lie form is parallel or not?
Your transversal geometry here. So if your transversal geometry, you need to have a constant Ricci curvature. Or yes, yeah, I think so. For if you want this equation to be satisfied, and if your theta is parallel.
But theta parallel implies Ricci 0 in the right. Okay. Okay.
Yeah, I think it only works. This equation could only be satisfied on the Hopf surface. Locally isomorphic.
Yeah, I initially thought that these Weissman metrics were going to be solitons, but well, it's just not true. I mean, I guess it's basically because Yuri said it's like the transverse geometry would need to be the round sphere, and it's both Weissman and the transverse geometry is the round sphere. It's only standard Hopf. That's the only example.
The question is, so one question which we will not be able to answer today, but it's a question which is definitely very interesting in, and we have an expected answer. What pluriclosed flow does on some arbitrary Hopf surface. with some initial metric G. Similar question, which is possible to answer, is.
Can you see what is the expected answer to this?
So let me write the second question and I write the expected answer. Do they exist solitons on G alpha beta? So today we will answer the second question. We explain that on all such Hopf surfaces there exists a gradient steady soliton, and the expectation is that whichever initial data you'll have, whichever Fourier-closed metric you take, which is compatible with this complex structure, it will always converge to this soliton metric. So that's the expectation. But again, so far we don't have really any means. Not that any means, but we're still lacking the some ingredients to prove it. So the next question, which we might also ask, which I discussed a bit today, if you're able to construct solitons and prove existence, what you can tell about uniqueness. And it's also, if you just work with Fourier-closed structures, we don't really know. We expect that they're unique, but we can't prove it. But in some cases, under some extra assumptions, which would involve generalized scalar structures, we are able to prove uniqueness, and I hope to be able to discuss it first briefly today. Construction of solitons. So the key feature which allows us to work with Hopf surfaces is their large group of symmetry. So if you take Hopf surface, which I recall C2 minus the origin modulo this group gamma generated by contractions, so this is your manifold M, then you can take group C star squared and act on it by coordinate-wise multiplication. So multiply the first coordinate and the second coordinate independently. So this gives you an action of this group on M. Now this action is effective on C star minus the origin, but it's not effective on M itself. So really what you get is the action of the group C star squared modulo gamma. And it is isomorphic as Lie group to R times S1 cube. So in particular, what we have here is a large compact group acting on this manifold. Now, if we believe that Fourier-closed flow does converge to the solitons, which we haven't constructed yet, and using the uniqueness of the solution to the Fourier-closed flow, it is reasonable to expect that the solitons which we're looking for, they must be invariant under this maximal complex subgroup of automorphisms of the Hopf surface. Indeed, what you can do, you can start with any Fourier-closed metric here, and you can average it with respect to this compact group, then you will have a metric which is invariant under this S1 cube. And along the flow, you will still have this invariance. And if you expect that the flow does converge to the soliton, your soliton metric will be also invariant under this group. So the idea is we should be able to, if solitons exist, we should be able to find them among metrics with the largest symmetry.
Can you explain? I didn't quite understand the argument. I understand that if you have a metric, then you could average it, and if you had a solution to the flow, you could also average that. But why does that show that the plural?
No, solution you can't average really, right? So if you have a solution starting with a non-invariant metric and you average a solution at every time slice, it will not be the solution to the Fourier-closed flow. But what you can do, indeed, you can take an invariant metric here, right? So you can take a metric which is invariant under this maximal complex subgroup. And you can run a flow starting with this metric. So if your initial metric is invariant under the maximal compact group acting on M, then along your solution, due to uniqueness of the flow, at every moment of time and every time slice, your metric will be invariant under this group. And now, again, it's not a mathematical proof, it's just explanation for why it's reasonable to look for invariant metrics. And the reason is that if you believe that your flow does converge to a soliton as time goes to infinity, then that soliton will also acquire this maximal symmetry group. So let's just start looking for solitons among the matrix with the maximal symmetry group.
So you're in the Keller case. There is actually an argument that a soliton, Keller-Ricci soliton, has to be invariant under the maximal compact subgroup. It's a variation of Calabi's original argument for constant curvature Keller metrics.
So does it work in any dimension, or is it?
It works in any dimension. Perhaps something similar going on here, that you can actually a priori prove that you have a soliton, it must be maximally symmetric.
Mm-hmm.
Not all of them, but you know, the group of isometry of the soliton has to be a maximal compact subgroup in the automorphism group.
Yes, that's the expectation. Yeah, that I didn't really know this argument from it.
Yeah, we can discuss it, but yeah, this is.
Is it maximal compact in the group of symmetries of the complex manifold?
Yes, that's right. That's the
yeah.
Usually.
Thanks.
So, yeah, expectation that the solid matrix will be invariant under this maximal compact subgroup. Now, this is three-dimensional group acting on something four-dimensional. So at least locally, what it gives us, so if this is your manifold, and you have the orbits of your S1 to the cube action, then in the transfers to this action, you really have only one coordinate. So you should be able to describe all the geometric quantities which you have here in terms of one real variable. And the equation, the Solomon equation, you should also be able to write down in terms of this one real variable. It will give you some system of ordinary differential equations for a function in one real variable. Well, what I have described here is really a local picture, but the structure of Hopf surface allows to make it global. So maybe I'll just briefly write down what's going on here without going into too much calculations and details. So what you can do, you can choose logarithmic coordinates on this space. So assume that our coordinates here are Z1 and Z2. So we choose logarithmic coordinates, logarithm of Z1 and logarithm of Z2. So you can assume that we are throwing away 0 sets of Z1 and Z2, and we take universal cover of the remaining thing. Take logarithm coordinates there. But really, a bit more convenient to us will be to choose some linear combination of these logarithmic coordinates. Sorry, let me write down, then I will explain it in this. So the B is log norm of beta, and K is log norm of alpha. So in these logarithmic coordinates, what you end up having, that everything depends only on real part of U1 and doesn't depend on anything else if you impose this symmetry along S1 cube. And in particular, a nice thing which you also will have, that such any structure, any invariant metric under the maximal action maximal compact group will also have a holomorphic complex holomorphic Killing vector field. So maybe I'll write it as a separate part. So in logarithmic coordinates, you can first write your metric kind of arbitrarily. You just choose this. Any Hermitian metric on these coordinates.
So, sorry, I got confused. So the logarithmic coordinates are on C2.
So you take the open dense part here, removing the loci with Z1 or Z2 equals 0, and then you take universal cover of it.
Okay, and
that's where logarithmic.
You're describing the metric on the universal covering.
Yes. Yes. So now you should ask yourself, what is pluriclosed condition in terms of this metric? And it happens to have a very clean characterization, and I formulated this as maybe a remark. So there exists.
Sorry, what are K, P, and M? Can you say it?
K, and P are smooth functions of real part of U1.
Okay, thanks.
So in this picture, this X is a real part of U1, and everything is invariant in this transversal direction. So there exists a holomorphic Killing vector field X. So it's a complex vector field of type 1, 0, which lives in the Lie algebra of this torus intersected with its image under complex, the operator of complex structure.
So when you say holomorphic and Killing in of type 1, 0, I got completely confused. So
so maybe I should call it bi-Killing. I don't know, does it help? So it has real part and imaginary part, and they're both Killing.
they're both Killing and they're both yeah, okay.
So it follows immediately from this large group of symmetry which we have. And under the existence of such vector field, the metric omega is pluriclosed if and only if G of X bar is constant on a compact manifold. Again, this follows just from this large group of symmetry existence of such holomorphic bi-Killing vector field, and this is just a direct calculation. Maybe I formulate now an existence result that Soliton equations on C2 with coordinates U1, U2, which covers C star squared with coordinates Z1, Z2, plus boundary conditions, which ensure that the resulting metrics and the resulting tensors extend to the loci with Z1 or Z2 equals 0. imply that for the metric G above, you will have n equals k, m equals 0, and k will solve an ODE, which reads as follows: k prime equals and conversely, such k yields a metric G which extends to the entire Hopf surface and solves the Sullivan equation v omega I equals rho I b smooth 1 1.
So is X common to all these metrics, or there is a killing?
The vector field X?
Yeah, I guess it depends on the metric, right?
No, it doesn't. It depends on the complex structure. So X depends on the complex structure. And if you assume that you're working with metrics which are invariant under the maximal complex group of automorphisms of the complex structures, then this one vector field will be killing for all of them.
Okay.
So is that the V in your if and only if condition?
No, here it's X. So X preserves the metric. X is a killing vector field, and here vector field V does not preserve the metric.
I meant the V from the first slide where you characterize the solitons.
Yes, that's the V.
And this V is just an element of the Lie algebra of S13. And
no, it's actually this V lies in this R direction.
Well, sorry, I meant IV. IV is the killing, right?
Yes, IV is killing.
Yeah, so IV is a specific element of S13, and it is determined from the complex structure. You say is that what the claim is?
So sorry, can you ask again? What's the question?
Can you determine IV in terms of the complex structure without knowing any equations at all?
No, I don't think so. You can. No, you can. Yeah, I mean, it requires calculation. So you can, after all, after you know the solution, but without knowing the solution, I don't know the method to identifying IV inside of this Lie algebra.
I'm asking because another feature of the Keller-Ricci solitons is that you do know the soliton field in advance. Once you fix the maximal compact subgroup, then it gives you automatically the soliton vector field.
Mm-hmm. Yeah, that would be interesting to understand here as well. I actually agree. This is something I still feel we don't have good understanding in all the solving constructions, and it will definitely clarify some of the points. So maybe let's discuss it.
I don't understand what is the thing that's difficult to see, because isn't V determined by that group because it's the generator of the R action?
Yeah, but the problem is that you can
well, there is only
there is no canonical choice of this splitting.
But there is only one V which will be the soliton.
Yes. Yes.
You could modify, as Yuri explained. If you have the soliton guy, you can modify by any symmetry and still have the two conditions, but only one will have this condition with theta
Yes, theta and grad f.
Theta and
Yeah,
grad f.
the real problem is that this identification is not canonical. Maybe I should write it equal. I should write it isomorphic.
Also, could you say what is P? You had in the description of the metric another function.
Yeah, P will be determined by this condition. P essentially will be constant. So let me maybe rewrite this metric in more familiar coordinates. So in Z1.
Sorry,
yeah.
This is more a question for Besti. So what you were saying is related to this fact that on an extreme Keller metric, the vector field given by the scalar curvature is uniquely determined by the complex structure. Is it?
Yes, and the same is true for solitons.
Okay,
Keller solitons as well. Yes, that's the claim. Yeah, so this is scalar solitons. You can see them as some sort of a weighted extremal matrix, and then the same argument applies.
It definitely will be helpful to see, like, canonically what IV here is. IV is here. So in Z1, Z2 coordinates, actually you can write this metric and it will look much nicer. Maybe I call it GS for soliton, and up to scaling it will have a form 0, 0, A over B, 1 minus K over Z2 squared. So where again K solves this a bit strange OD, so it's fairly explicit. It's inverse of some explicit. K will be inverse of some explicit function because this OD can be explicitly integrated.
So K is a function on Z1 square and Z2 square. Is that, or it will be?
No, K is a function of real part of B over A log Z1 minus log Z2. So as written, it is defined only where Z1 and Z2 is not zero, and the claim that these quantities extends as smooth functions to the entire manifold. Does it make sense? So maybe let's do concrete examples. For example, and let's see that we can recover what we know from for the round Hopf surface. So if norm of A equals norm of B, then you can solve explicitly this OD. It will be simpler because this just vanishes, and this will be 1. And the solution to this OD K of X will be one of the solutions because there is a constant of integration. So we can integrate this some choice. So actually here it's better to put two real parts. Not better. I mean, for this formula to hold, I want to put 2 real parts. Probably also messed up with signs here. Oh, no, it's correct. So this is your K of X, and you can just substitute back into the expression for G and observe directly that it will be the round metric which we expected to have. So now let me get back to generalized scalar structures. So again, it's the expectation here in the same spirit as why we expect for the solid metrics to be maximally invariant. And it could be formulated as follows. We know that fully closed flow preserves generalized scalar structure. So specifically, if you start with some pluriclosed structure, MGI, and you extend it to the generalized scalar structure, and I just think of generalized scalar structure here as in this bi-Hermitian description, which we have seen before. So it's a GK structure. Then pluriclosed flow for MGI extends to a GK structure with G at time t being just a pullback of the initial structure along appropriate one-parameter family of diffeomorphisms. So if your initial data can be extended to a generalized scalar structure, you expect that the limit also will have generalized scalar structure, because at least it is true along the flow at all points. Again, it's not a mathematical statement, but it's an expectation of what types of structures you should be able to obtain as limits of your flow. And we happen to know that Hopf surfaces do have compatible generalized scalar structures, and so we expect that this limiting metric which we obtained here will be also compatible with generalized scalar structures. And it happens to be so in actually two distinct ways. And let me describe these two distinct ways separately. Let me start with odd GK structures. So in this case, it really just means that I and J commute, and I is not plus or minus J. So there is such structure in Hopf surface, and it could be easily described. So we start with C2 minus the origin. We have quotient it by gamma, and this is induces one complex structure, which I called I alpha beta. But you can also flip orientation in one of the factors. One of the factors. Basically, you think about it as C cross C with inverse orientation minus the origin. And you quotient by the same gamma. And it gives you a second complex structure with parameters alpha and beta conjugate.
Is that the same as taking the opposite?
Opposite in one of the coordinates, yes. This has the coordinates. You have minus J in one of the coordinates, minus I alpha beta. So this describes two complex structures. Now you need to describe a compatible metric, but any compatible metric, any metric which is diagonal in these coordinates will be compatible with both I and J. So any metric G in Z1, Z2 coordinates, which looks like this, is compatible with both of them. And by again conformally modifying it, you can make it pluriclosed. So then this data, these two complex structures and this metric will define odd type generalized scalar structure in a Hopf surface, and you expect that it will survive to the limiting soliton. And if you look at what we got as our formula for soliton, it is exactly of this form. It is of a diagonal form. So this whole discussion sort of explains that we could have from the very beginning imposed this to be 0 if we were just looking for solutions. Because from the very beginning, it was very reasonable to expect that the metric, the Sullivan metric, which we will be able to construct, if we are able to construct it, should be compatible with this generalized scalar structure with these two complex structures I and J.
Yuri, sorry, to get this odd general scalar structure, don't you need to ensure that the leaf forms of the two are the same?
But if you take any pluriclosed metric with respect to I and J, they will be the same. If they correspond, if I and J already define a splitting.
You need that a diagonal, the stars are depend only on Z1 and the other on Z2?
No, you don't need that.
Are you telling me that any metric that has this form?
Yes.
But that's not true, I think.
I mean, in a sense, the leaf form is sort of like degree 2 in the complex structure. It appears once in the Kähler form, and then
multiply this by a conformal factor, and it will not satisfy.
So, sorry?
I can multiply such a diagonal metric by any conformal factor, and I don't think that the leaf forms will stay.
No, but I choose conformal factor for it to be pluriclosed.
Mm-hmm.
Yeah, basically, if your G has a form like U00V, then your omega I will be U dz1 wedge dz1 bar plus V dz1 dz2 dz2 bar, and your omega J will be dz1 bar minus V dz2 bar. And then from these differentials, you should obtain that the leaf form from the differentials of omega I and omega J, the leaf forms coincide. Actually, maybe you even don't need the G split close.
Yeah, I think you need to make sure that the leaf forms coincide.
Okay, let me move on and describe the second the even GK. So it was actually made explicit by Marco for the standard for A equals B, and it sort of could be explicitly derived, but was implicit in Marco's discussion of T duality on Hopf surfaces, the existence of such even GK structure on Hopf surfaces. But the way they actually appear evidently is through the Sullivan construction, and we sort of guessed what this should be from the given matrix. So to define two complex structures, it's enough to define two zero forms for both of them. So 2-0 form for the standard complex structure is this logarithmic symplectic form. And it defines a complex structure in the open dense set of C2 minus the origin, and it extends everywhere on the Hopf surface. So this defines I alpha beta as the unique complex structure such that this complex form is of type 2, complex valued form is of type 2, 0. And you can write it again, a fairly explicit formula omega plus, which would define the compatible second complex structure, and this omega plus, let me write it down. So k is the same function k as before. So yeah, perhaps it's not super illuminating, but it's fairly explicit. And this gives you J alpha beta bar. So, and these two have common real parts. Real part of omega minus equals real part of omega plus. And imaginary part of omega plus gives you omega I, and imaginary part of omega minus gives you omega j. And with this description of generalized scalar, even type generalized scalar structure, you can actually have a nice interpretation of this function k through generalized scalar world. So this function k is actually nothing more as just the angle function up to change up to linear transformation. So just make a remark that if you introduce consider function 1 minus 2k and you denote it p, and this is exactly minus 4 trace of ij. So this function k has an explicit interpretation. So maybe let me move to uniqueness questions. Are there any questions at this point?
Is it right? This gives you two different generalized scalar structures that have the same soliton?
Yes, that's true. Yeah, you have two different generalized scalar structures. One is of odd type, another is of even type, and they both are compatible with the soliton, with the pluricose soliton.
Also,
Yeah,
how? Oh, sorry.
Go ahead.
Which in this case is just the round Hopf metric, right? That's all we're talking about.
Say again, sorry.
Which in this case you're mentioning here is just the round Hopf metric.
No, that's for diagonal. This for diagonal, for any diagonal soliton.
Oh, sorry, you wrote down the general one. Sorry.
Yeah.
Did you guess the second structure of even type? It's just is there in any kind of a systematic way to write these things, or are you just?
Yes, sort of. Yeah, there is a way. So there was one discovered by Marco for A equals B, and you just kind of looking at it carefully and finding explicitly two holomorphic coordinates like this. It's very suggestive what you need to change to make it compatible with this solutons. But yeah, I don't have any kind of good explanation which avoids any calculation and guessing whatsoever.
I just probably want to mention that for A equal to B, there was old papers that discovered two hyper complex structures with oppositely forms. So it's really kind of was known in the 90s.
I see. Yeah.
Theory literature, this phenomenon. And it was used, by the way. It's important.
What paper is this, Vesti?
I think there is a paper by Goduchon of Weil structures of type S1, S3.
Oh, that one. Okay, yeah, I know.
Yeah, it's an old paper, but it's a prominent example.
Mm.
Well, and I guess also just as a further remark, like when A equals B, there is this nice geometric description of how you're getting the second complex structure, right? Using the inversion.
The inversion.
Yeah.
So yeah, this also could be described this way. It will be sort of generalized inversion. You will have, instead of inversion as in a round sphere, you will still have inversion sort of in some three-dimensional shell in this Hopf surface.
And so the second structure is of type alpha beta bar, you say? Or?
Yeah, it's, I mean, depending on the choices of signs here, it will be either alpha beta bar or alpha bar beta.
Wait, sorry, Yuri, are you saying that this this inversion trick, there literally is a map? Is this thing the pullback by an actual map defined on?
Yes, yes.
But alpha beta bar, is it biholomorphic to alpha beta?
No, it's not bihomorphic.
So inversion in a very relative sense. It's not.
Yeah,
it's not a dysmorphism that sends one to the other.
Yeah, inversion changes the orientation, right? And here I and J have the same orientation. So what really you need to do in the round case, you take inversion in the round free sphere, and then you compose it with a reflection in Z1 equals 0 or Z2 equals 0. It's your choice. And you pull back by this map, and this map already preserves the orientation. So you'll get a second complex structure with the same orientation, and as an underlying complex manifold, we'll have parameters alpha and beta bar. And these can be described similarly, but again, instead of inversion, it will be a more complex map, which is defined through this function K. So now let me briefly maybe write down several questions about uniqueness and maybe then formulate some results. So
what do you know about this even GK structure? I mean, I guess this is not commuting type, or
yeah, they're not commuting. You have this Poisson tensor, which is non-zero generically, and it vanishes at two elliptic curves, which you have on any Hopf surface. So on any Hopf surface, you have elliptic curve where Z1 equals 0 and the other one Z2 equals 0. So they degenerate, sigma Poisson tensor degenerates there. Yeah, and other than that, I don't think we know much about this general scale structure. I mean, what could you know? What questions could you ask? Actually, I don't know. So yeah, but the picture, the way we think about it, so maybe this rough picture, if this is your C2 minus the origin, and you quotient it by contractions, and your fundamental region is this sort of annulus with two boundaries glued together. And inside you have these two elliptic curves. The one where I equals J, and the other is where I equals negative J. And here I commutator of I and J is invertible in the middle. So this is about uniqueness, and for about existence. So for uniqueness, there are many questions which we don't know the answer yet. So question 1 is prove uniqueness of pluriclosed soliton on Hopf surface. So we don't really know how to approach it. So next question which you could ask is, well, maybe not pluriclosed soliton, maybe we also additionally impose generalized scalar structures. So prove uniqueness of generalized scalar Ricci soliton on M I alpha beta and then some complex structure which you don't know. And this part actually breaks into two questions which are generally separate. Is one about even generalized scalar structure and one about odd generalized scalar structures. So, and this even question, this one is open. We don't know. We have some ideas how to approach it using essentially some of the toric structure behind this entire picture, but we don't know. Maybe I'll just mention that in this case, you will have two key-length vector fields, and this seems to be useful. You will have I theta I sharp minus grad f, and you will also have j theta j sharp minus grad f. And the fact that they are a priori two key-length vector fields is helpful.
And theta j is minus theta I.
Yes, and these are opposite each other. Theta I is negative theta 2 in even case. So yeah, they are genuinely different. And
I guess
yeah, go ahead.
I was gonna say the J star must be like I alpha beta bar, right? Just because, or well, okay, sorry, maybe you mean in general dimensions. I guess in dimension 4, that's the only possibility. Right? Or no, yeah, you're
Why?
Yeah.
That?
Isn't that, I thought that followed from your work, Vesti. I thought the only possible compatible generalized scalar at all, forget the soliton equation, was I alpha beta bar. Is that not right?
I don't know. I forgot. So if you know that,
I think this.
Yeah, I also thought it
I'll
follows.
tell you which paper of yours it's in later.
Yeah, I thought it should follow.
I have written stuff like this, but I don't remember. But
think,
yeah, so you not have this class 2 surfaces, which are just deformations of diagonals.
Well, no, but those don't emit GK at all, right? Because they only have one elliptic curve, right? And so you cannot have the p equals.
Oh, that's the thing. Oh, yeah, I see. Okay, yeah, then you're right.
You must have both vanishing.
Yeah.
Also.
Well, yeah. So yeah, on the Hopf surface, yeah, Jeff. Maybe I should mention that it should be either alpha beta bar or
like minus the
alpha bar beta.
Is the same alphabet necessary?
Yes.
Yeah.
Yeah, because those are defined on the alpha and beta parameters. Alpha and beta could be read off from the moduli of the elliptic curves.
From the anti-canonical divisor.
Yes, from the anti-canonical
divisor. Exactly.
Yes. So maybe let me briefly mention the uniqueness in the odd case, because it's interesting and it brings together some interesting homological considerations for odd type GK structures. So recall this definition which Jeff made 2 lectures ago, that we can define formal GK structures. Okay, maybe let me set the background. So we assume here that I commutes with J, and I is not equal to plus or minus J. So this defines you a splitting of your tangent bundle at any point. Into the eigenvalues plus and minus eigenvalues of the product of I and J. And formal generalized scalar structure will be a collection of tensors in lambda 1 1 of I, real tensors, such that first DDCI at I is 0, and second that you can define at a J. So satisfies DCJ at a J equals negative DCI at I. So these are all the conditions which you put on generalized scalar metric except for positivity, right? It's pluriclosed, and you have this compatibility of two torsions, but you don't impose condition that this is positive definite. And you can set up a homology space. Which we denote by H. So this will be the set of eta
Sorry,
I.
Can you
Yes.
say how do you define eta j? So it's minus eta I, and so what is in the first entry?
Yeah, this is this operator pi, which Jeff introduced, I think, last time. It's just a product of
Oh,
R and
sorry,
J.
sorry. I didn't see it.
So you consider collection of all 1-1 forms which are formally GK, modular the this special Laplacians of functions. I explain in a second what it means. Not Laplacians, actually, in some of these twisted fashions. So this square f is del plus bar minus del minus bar of f, where these are del and del bar operators in these two opposite subspaces. This is L minus, this is L plus, and in each of them you have their own its own del and del bar operators. So there is a general argument which is fairly straightforward application of maximum principle, which can be stated as follows. So if you have, this actually works in any dimension. If you fix the complex structures I and J, and you have two solitons with joint vector field V, and the omega I for one of them represents the same class as omega 2 and omega I for the other one. So you assume that these cohomology classes in H are the same, and you assume that the Soliton vector fields are the same for the two solitons. Then you can conclude that G1 equals G2. So here we assume that M is compact.
Are they solitons for, like G1 is a soliton for I and G2 is a soliton?
No, sorry. It's an odd type GK structure. So these are two complex structures which commute with each other, and there are two metrics which are compatible with both of them, such that the resulting two structures are both odd type generalized scalar structures.
Yeah, so when you write this D plus bar and everything, so you need to have some sort of splitting of the
Yes,
bundle of holomorphic bits which are integrable.
that's right. Yes. Yeah, maybe I was a bit sloppy. Yeah, so we assume that I and J are defined on that there exists a foliation by L plus and L minus, and I and J coincide on L plus, and they are opposite on L minus, and where L plus and L minus is a holomorphic foliation with respect to both of them.
And when you say uniqueness, it's up to some automorphism group or really?
No, just unique on the nodes. So, and proof goes essentially as follows. So we assume that omega 2i is omega 1i plus this operator on some function u, and then soliton equations plus maximum principal, elliptic maximal principal, imply that U is constant.
Sorry, can you say what are the generalized scalar Ricci solenoid equations, because I think you did not define them.
Right. So yeah, in this case, yeah. So what you really need here is something even less than this generalized scalar solidon. What you need, that with respect to this vector field, you have that the derivative of omega I equals rho bismuth I11, and the derivative with respect to the same vector field of omega j is rho bismuth j11, which both are implied by the assumption that mgi and mgj are pluriclose solitons with the same F.
And what is the assumption on V here?
So here you don't need any assumption except for that it's holomorphic with respect to I and J.
But what is the relation with the two Lie forms? In general, I mean.
If your convex structures are defined as they're defined in the odd case on the so again, maybe let me repeat myself. So the standing assumption here is that we have this foliation into L plus and L minus, and I and J's coincide in L plus and the opposite on L minus, and this metric G is compatible with both of them. Then in this case, Lie forms, well, actually, so yes, I mentioned dimension 2, it implies that they're the same. In higher dimensions,
Yeah, I think that the torsion forms will be related.
no, but torsion forms will not be the same. The torsion, I mean, yeah, torsion forms are opposite to each other as always.
Mm.
But yeah, Lie forms. Yes, actually, yeah, I'm not sure what would be the relation for the Lie forms here.
In 4 dimensions, they are the same, as you said.
Yeah, in 4 dimensions they're the same.
But are you using at all this condition for V, that it's Lie form plus gradient?
No, what I need that it's holomorphic with respect to I and J.
Yeah, I mean, the key point in this, or I don't know if you're going to prove it or not, Yuri, but it's really this like kind of transgression formula for the Bismuth Ricci that you end up using.
Yeah.
To basically get a Monge-Ampère equation for U.
So it's essential that we are a steady soliton and not.
Yeah, exactly. So it becomes more like sort of a Calabi-Yau case rather than Kähler-Einstein.
Yes. Okay, so maybe let me, yeah, I really, I'm gonna finish like in a couple of minutes. I just want to finish this uniqueness discussion. So maybe next proposition, which I don't really have time to discuss, but for an odd type GK structure on OP, that is M, I alpha beta, and J alpha beta bar, we have the dimension of this homology space it's two-dimensional. Its real dimension is 2. And it implies that the action of this torus on H is trivial. Yeah, I denote this as concrete. So it fixes every cohomology class. And then I can formulate a theorem. If and for I alpha beta J alpha beta bar G is an odd GK soliton on a Hopf surface, then G is S1 torus invariant. And in particular, since we described all the solitons with a maximal symmetry, our construction of solitons with maximal symmetry is exhaustive. G is isomorphic to the pullback of the soliton, which we have constructed by the diffeomorphism generated by the soliton vector field. And the key input here is, of course, the key fact here that G must be a priori invariant under the maximal group of automorphisms of the complex structures. And this follows from the fact, from the uniqueness and the fact that, sort of from this general uniqueness above, and the fact that the action of the torus fixes all cohomology classes in the relevant homology space. So yeah, I'm running out of time, so probably I'll stop here, and I'll continue next time with this discussing complete solitons on dimension 4. And the reason again why we're interested in complete solitons, because supposedly they occur as limiting objects of fluid closed flow and generalized Kähler flow on compact surfaces.
Yeah, thanks, Yuri.